Hello everyone, welcome to part 2 of lecture number 2. So I hope that at this point you had the opportunity to go through the slides or the last lecture as well as through the text. Um, in this part of the second lecture, we're gonna solve a number of numericals and um, the idea is I want you to practice whatever you've learned during our last lecture. Now, this first example that we are going to look at is more of a direct stiffness um, approach example. Don't worry if you don't understand whatever I'm doing in this on this slide, because strictly speaking, direct stiffness approach is not the topic of this course. And if you don't understand it, you can somewhat you know you can get away with it to an extent until we reach the multi-degree of freedom structures. So when I'm solving this example, my assumption is that you are familiar with the direct stiffness approach. Also, you need to understand the rotational stiffnesses and the shear rotational stiffnesses that we introduced and talked about in our last lecture. So the question is how to calculate the lateral stiffness of the frame. And step number one, as usual, is to locate the free degrees of freedom. Now, without any assumptions, the free degrees of freedom of this frame element are going to be 6. But since we are assuming that our columns and our beams are inextensible, therefore we're gonna assume that the lateral displacement of our top left node and our top right node are equal to each other, and also the nodes are not going to move in the vertical direction, assuming small deformations. So with these assumptions, the 6 free degrees of freedom reduced to 3 free degrees of freedom. The first free degree of freedom that we are talking about is the horizontal displacement of the roof of this frame. The second um, degree of freedom that we have identified is the rotation of the top left node. The third degree of freedom is a rotation of the top right node. The second moment of inertia of the beams and the columns are assumed to be equal to each other. So IB is equal to IC. The length of the frame is twice as much as its height. So since we have 3 free degrees of freedom, the KFF or the free stiffness matrix, the size of it is going to be 3 by 3. Now to fill up the first column of this matrix, what we have to realize is that this matrix is part of a simultaneous equation, a set of simultaneous equations. So on the left side, we have the force vector, and therefore if I associate my first degree of freedom with the horizontal force at the top given by Fh, my second degree of freedom with the moment, an anti-clockwise movement um, at, at the top left node given by M2, and similarly an anti-clockwise movement at the top right node given by M3, then my force vector would look like this. Each of those force quantities are going to be associated with the corresponding degrees of freedom. And the stiffness matrix, therefore, gives us a relationship between the left-hand side and the right-hand side. Now, to fill up the first column of this um, frame of this KFF, we need to impose a deformation on our frame whereby u1 is equal to 1 and theta 2 is equal to theta 3 is equal to 0. So when I do that, my deformed shape looks like the figure shown on this slide. The columns, each one of them is bending in double curvature and with the point of inflection at mid height. The the horizontal displacement of the top relative to the bottom is equal to 1, that is u1 is equal to 1. When we impose this deformed shape, we know that the resisting lateral force at the bottom of each of the columns is equal to 12 EI over h cube. Now, the total force that I have to apply at the top of the frame towards the right to balance these two reaction forces is twice as much as the shear induced at the bottom of the columns of this frame, right? So this comes out to be equal to 24 EI over h cube. Also, to prevent each one of the nodes from rotation, I have to apply a counterclockwise moment given by 6 EI over h square at the top left and the right nodes. Now, if I go back to my stiffness matrix and if I realize that this is all of these forces correspond to u1 is equal to 1, then I can fill up my first column by realizing that my shear force is 24 EI over h cube. My moment on the top left node is equal to 6 EI over h cube. My moment on the top right node is again 6 EI over h squared. Note that the moments that I am applying on the top nodes have IC, or the moment of inertia of the columns in them. They do not have the moment of inertia of the beam term in them because the beam would remain flexurally unstrained. Having filled the first column, we can now start working towards filling up of the second column. And to fill up the second column, our second degree of freedom, u2, is equal to 1, and our u1 is equal to u3 is equal to 0. If I impose this deformed shape on my frame element, I'll have the shape that is shown on this figure. For u2 is equal to 1, which means a single radian rotation in the counterclockwise direction on the top left node, I'll have to rotate my column by 1 radian in the anticlockwise direction, and I'll also have to rotate my beam in the same direction. So I have to apply a moment to rotate, to bend my column, and I also have to apply a moment to bend my beam. So the first term here is the force, is the moment that is required to bend my column by a single radian. And my second term here is the moment that is required to cause a single radian of rotation in my beam. Since L is equal to 2h, we can simplify this expression as 4EI over h plus 4EI over 2h, which is equal to 6EI over h. Now, when I rotate the top left node in the counterclockwise direction, and had I not fixed my top right node against rotation, it would have rotated in the clockwise direction. Something I would have had a deformed shape which would have looked something like that, right? Now, to prevent this top right node from rotating in the clockwise direction, I have to apply a moment in the counterclockwise direction, and the magnitude of that moment was worked out in our previous lecture, and we know that that is equal to the carryover factor of a prismatic member, and therefore we have that value equal to 2EI over 2EI over L. Since L is equal to H, we can again have EI over H as the final um, expression, since we are formulating the stiffness matrix in terms of H and not L. Now, when I rotated my top left node, I applied a moment equal to 4 EI C over H on my column to rotate it in by 1 radian rotation in the counterclockwise direction. When I did that, I had to apply a shear force at the support towards the left, and that shear force was equal to 6 EI over h squared. From where did this come from? Well, we talked about this in our previous lectures. Since this force was towards the left, the force that I have to apply the force that I have to apply at the roof level will be towards the right, and that force will be exactly the opposite of the force that we had at the bottom of my left column. So now I have all the three terms to fill up my second column. Again, what I'm doing is I am correlating my free stiffness matrix with my deformations and force quantities. So now I can actually go and fill this up, and this comes out to be 6 EI over H. My first row would be my 6 EI over H square from here, and my third row would be 2 EI over L or EI over H. So in a similar way, we can proceed and we can fill the third column using my third free degree of freedom. And if I do that, what I'll need to do is I need to rotate my top right node by a single radian rotation, and then this column would do this, and there will be a point of inflection over here. Please don't go into the curvatures of things that I'm drawing, because it's not gonna look like what I actually mean, because I'm really struggling to draw on the screen. And then we will have something like this, that, and the moment that I have to apply on my top right node is equal to EIC over H 4 times plus 4 times EIP over 2H. This is again going to be equal to 6 EI over H, right? When I am going to apply a moment to cause 1 radian of rotation on my top right node, I'll have to apply a shear force in this direction, and my shear force is gonna be equal to 6 EI C over H square. And I have to apply a moment in the counterclockwise direction on my top left node, and that moment is going to be equal to 2EIB over L, which is then equal to EI over H. So I can then fill up the rows and columns of my KFF, and I can simply go and see which of one of these is my forces, right? So this is this is my this is my this is my, and then I'm going to be doing this, right? So this is, one is 6EI over H square. My second row is my M2, which is EI over H. And my third row is equal to 6EI over H. So this gives me my complete stiffness matrix of the frame. Now, as we talked about, we were saying what our lateral stiffness of the frame is. And if I oops, I'm struggling here. Okay, so if I um, associate the rows with deformation, my first row will be my lateral displacement at the top, right? So this is going to be equal to 1 M2 and M3. So if I open up my first row, I'm going to get FH is equal to 12 EI over H cube U1 plus 6 EI over H squared U2 plus 6 EI over H squared U3. So for this to know, I need to know U2 and U3. So I know that my moments M2 and M3 are equal to 0 when I'm just trying to find my lateral stiffness of the frame. So the first thing that I have to do is to actually invert this and get U is equal to KFF inverse times F. And when I do that and carry out my actual inversion, which we can for symbolic, and I'm going to be too cumbersome and I'm not going to go all the way. And then if I sort of correlate my U1 with my FH, what I'll have is a row vector here, and that is my lateral stiffness. If you open Chopra actually does this in Chopra does this and he gets a value of K equal to 96 over 7 EI over H cube. Now, if you don't understand all of this, this example is actually more about that direct stiffness approach than the structural dynamics. This actually would be understandable to anyone who has current knowledge of direct stiffness approach. So if you don't understand this and if you want to skip this example, you're going to be fine for the time being. Now, let's consider an easier example. This has a lot less to do with structural mechanics than structural dynamics. Now, in this example, what we have is we have a structure and the unit weight on top of the structure is 30 pounds per square foot. The horizontal cross bracing is at the bottom chord of the roof trusses, which means not at the top, but right there. All columns are W8 by 24. The second moment of inertia is 2.4, 82.8 inch for IX, and IY is 18.3 inch for. The modulus of elasticity of steel is 29,000 ksi, and we are asked to formulate the governing equation of free vibration in the north-south and the east-west directions. Now let's consider the north-south direction first. In the north-south direction, the stiffness, the lateral stiffness of our structure is provided by only 4 columns. And we note that the major bending axis is along the north-south direction. So we know that I is equal to 82.8 inch 4 for the north-south direction. Since it was specified that the trusses are horizontally braced at the bottom level, um, that means that the columns are gonna be bent in double curvature, and there's going to be no rotation at the bottom level of the trusses as shown, as indicated in section elevation B shown above. So the length or the height of the columns that is going to contribute towards lateral stiffness is 12 feet. That means that my lateral stiffness of the structure is just equal to 4 times 12 EI columns over H cube, which is equal to 4, 12, 29,082.8 over 12 into 12 cube. Now this K then comes out to be equal to 38.58 kip per inch. Now this means that 38.58 kips have to be applied at the bottom of the truss level for the frame to deform in the north or the south direction by 1 inches. The next thing that we need to calculate is the mass. Now we are given that the roof level of the structure can be considered to resist 30 pounds per square foot. That means that the total weight at the roof level is nothing but 30 multiplied by the area of the roof. So and if we have to calculate the equivalent mass due to this weight, we need to divide this by the force by the acceleration due to gravity, because from high school we know that weight is equal to mass times this acceleration due to gravity. So this weight, which is 900 and which is like 18,000 pounds, gives us 46.63 pounds second square per inch. Note that our acceleration due to gravity in the units of inch per second square is 386. Once we have calculated the stiffness and the mass, we know that for a free vibrating system without any damping, the equation of motion becomes all we need to do now is to plug in the values of mass and stiffness. Now in the east-west direction, our structure um, consists of two vertical braces and two lines of vertical braces. We are going to neglect the resistance due to the columns of bending because it's negligible as compared to the stiffness of the vertical braces. Um, from structural mechanics, we know that for an axial element that makes an angle that is inclined at an angle of theta degrees with the horizontal, the stiffness of such a uh, um, truss element in the horizontal direction is A E over L multiplied by cos square theta. So we need to calculate L and we need to calculate theta. L is simply equal to 12 square plus 20 square under the root. Now 12 is the height of the vertical bracing. This comes out to be 23.3 feet. Theta then comes out to be cosine of theta then comes out to be 20 over L, which is equal to 20 over 23.3. So with these two quantities, we can then calculate the stiffness of the bracing in the horizontal direction, and that stiffness is equal to AE over L into cosine squared theta. A is equal to 0.785 inches. E is equal to 29,000. Length is equal to 23.3 into 12 inches. And cosine squared is equal to 20 over 23.3 squared. This comes out to be 59.8 tips per inch. Now only one of the vertical braces are going to contribute to resist the lateral displacement of the structure, and that vertical brace is the brace that goes into tension. The other vertical brace that goes into compression is simply going to buckle, and therefore it's not going to resist the lateral displacement of the top of the structure. So the K value that we have just calculated for the brace is has to be multiplied by 2, um, and we get our lateral stiffness value of the frame in the east-west direction. So this is 119.6 Gibbs per inch. My mass has already been calculated, and that was given by 46.6 pound square per inch, which is equal to 0.0463 Gibbs second square per inch. So I know my mass and I know my stiffness, and I know that for a freely vibrating dampless system, the equation of motion is given by all I need to do is to plug in those values of mass and stiffness into this equation. Again, we are neglecting the lateral stiffness of the structure due to flexural bending of the columns. Next, consider an example where we have a mass M hanging by a cantilever via spring. We are asked to formulate the equation of motion of this mass M. The length of the cantilever is 10 feet. The diameter of the cantilever beam is 2 inches. The mass M is acted upon by a force that varies with time, and that force is Pt. The spring constant of the spring is 20 pounds per inch. Note that in this case, the mass M distance in the vertical direction can be calculated with respect to the support, in which case it is given by u bar, or with respect to the position of static equilibrium of the mass, in which case it is given by u. Note that u bar is related to u via this equation, where delta static is the vertical displacement of the mass under constant static vertical self-weight load. Consider the vertical equilibrium of mass M as shown in figure C on this slide. If we write the vertical equilibrium equation and fill in all the values, we'll have W plus PT is equal to Fs plus Mu bar dot dot. Now U bar is the displacement of the mass relative to the support of the cantilever beam. From the previous slide, we know that U bar is equal to U plus delta static. Delta static being the static equilibrium deflection of the mass. And if I take twice the derivative of this equation with respect to time on both sides, I'll have U bar dot dot is equal to U dot dot. Why? Because delta static is constant with respect to time. Also, I can write my spring force or my spring resistance force as Fs is equal to Ke times U bar. Now Ke is the equivalent stiffness of the cantilever spring system in the vertical direction. We don't know that, we will calculate it. Again substituting U bar into this equation, we get Ke U plus delta static. Plugging in the value of U bar dot dot and Fs into equation 0 from equation 1 and 2, we get now if we open up both sides, we open up the round bracket, we'll get in the above equation the equivalent stiffness multiplied by the static displacement of the mass in the vertical direction is nothing but the self-weight of the mass. So this term cancels with that and we are left with note that in equation 3 we have converted everything from the U bar coordinates to the U coordinates, and the U coordinate is relative to the static equilibrium position of the mass. So equation 3 is independent of the independent of the coordinate system U bar. The last remaining thing that is left is to calculate Ke. Now Ke can be calculated by considering that my total vertical displacement of the mass is due to two sort of springs. The first spring is my cantilever of 2 inches diameter and 10 feet long. From statics, I know that the vertical displacement of this of a cantilever at the tip uh, due to a single kip force is nothing but equal to 3 EI over L cube. So, in other words, my K cantilever I over L equals 6. So this is one of the two springs. The other spring is by 20 pounds, 20 pounds per inch, and that spring is actually at the end of the cantilever. When I was calling my cantilever a spring, it was actually metaphorically saying that it is a spring. It is obviously a deformable structural element, and therefore it has its own stiffness. Now, the total deformation of the two springs in series is deformation of the spring plus deformation of the cantilever, right? Now, this total deformation is u bar, right? So this is the same u that I have over there on the other slide. And so if I plug in my values of stiffness and force, what I'll end up is I'll get from this equation is Fs over Ke. Fs is the same force, my spring force Fs is equal to Fs over K cant plus Fs over K spring. Now, all I need to do is I need to plug in values of my K cantilever, which I have already worked out up there, which is 39.54. My K spring, which is 20 pounds per inch. And Fs appears on both sides of this equation, so Fs cancels out. And I'm going to apologize for jumbling this up. And if I do that, I end up with my K equal to I want to evaluate this value. This comes out to be 13.39 pounds per. So now I have the value of everything that I need in this equation. I have mass m, which is the problem, and I have my u relative to the static equilibrium position. Next, consider a structural system that consists of mass m on top of a rigid column. The rigid column is connected to the base through the spring K. The length of the rigid column is L. The mass m is due to the weight of the body W at top of the rigid column. We are asked to derive the equation of motion due to rotation of the rigid column about its base. Now, from D'Alembert's principle, we know that there is a virtual inertial force in the direction opposite to the acceleration of the mass m. If we characterize the deformation of this system by an angle theta with the vertical, then we can write the inertial force in the mass m as now L is the length of the cantilever, and theta dot dot is the second derivative of the rotation function with respect to time t. The other force that is acting on top of the cantilever is due to the self-weight W, and that is simply equal to W itself. The third force that exists at the base of the cantilever is due to the rotational spring K, and that force is given by K times theta. Taking the sum of moments about the base of this cantilever, we get now for very small angles theta, sine of theta is approximately equal to theta itself. So the above equation becomes and plugging in the value of Fi, we get so this is then the equation of motion of the system about the base um, of the cantilever. Consider a three-dimensional single-story frame shown in this figure. The ground is rotating about the vertical axis through O. The frame consists of a rigid slab that is supported on top of four columns of height h. The mass of the rigid slab is m. The second moment of inertia of the columns about the x and the y axis are given by Ix and Iy. We are asked to determine the equation of motion of the three-dimensional single-story frame with respect to the vertical axis passing through O. Or in other words, we are asked to formulate the equation of motion of the frame about the torsional degree of freedom direction. Now, we need to understand two concepts before we start to solve this example. The first concept is that we need to note that the inertial effects in the slab are due to two components of motion. The first component is the displacement of the ground, or is the rotation of the ground with respect to a fixed frame of reference that does not move as a function of time. So we if we characterize this displacement or this rotation of the ground relative to the fixed reference by a variable theta g, then we need to consider the fact that the top of the frame also deforms with respect to the ground, and therefore if we add that component designated by a variable theta, the total rotation of the top of the single story frame with respect to the fixed reference comes out to be theta t. If I take the second derivative of this equation on with respect to time t on both sides, we end up with the second um, the second information that we need to know is that the torsional inertial moment about the centroidal vertical axis through O is given by Fi is equal to mass, which is the total mass of the slab, multiplied by IO multiplied by theta t dot dot. Now IO is the second moment of inertia of the slab about the vertical axis. This can be calculated using calculus and is given by b square plus d square over 12, where b and d are the breadth and the depth dimension, or the length and the width of the slab. So if I open this up, my total inertial moment about O will come out to be this quantity, this equation. Next, having calculated the inertial effects about O, we need to calculate the stiffness response of a three-dimensional frame about the torsional degree of freedom through the vertical axis at O. In order to calculate the stiffness response of the slab about the vertical axis through O, consider the figure that shows the plan view of the deformed slab on this slide. Now, if the slab rotates by a single radian about O, each of the columns connected to the edges or the corners of this slab will be deformed in the x and the y directions. When this happens, and if we label, um, if we label the dimensions on the plan here, So D is along the vertical axis and B is along the x-axis. And if I rotate the slab about the vertical axis by a single radian, my deformation in the vertical direction is given by B over 2 as underlined on this figure. Note that the sum of vertical deformations in the columns add up to be equal to 0. Similarly, for the same rotation, my, my columns will translate in the horizontal direction by a magnitude d by 2. Now these columns, the horizontal deformation also adds up to be equal to 0, which means that if my columns are of the same dimensions and if all of the columns are prismatic, then the rotation through O will not cause the slab to translate in any of those directions. Once I have calculated the horizontal and the vertical deformations of the top of the columns, I can simply multiply this deformation with the stiffness of the columns in the x direction and the y direction to get the corresponding forces. This has been shown on this figure along with the direction of the force. Each one of those forces have a moment about O, and we can calculate that easily since horizontal contribution of the moment and the vertical contribution of the moment of each of these columns is equal to each other. We can simply write the resistance of the slab due to single radian rotation as note the product of the first two quantities is the force, and force multiplied by the third quantity inside the round brackets is the moment. Four is used to scale up or multiply the response of a single column and consider the effect of all of the four columns because all of the four columns are identical to each other. So I can then simply use this k theta along with the Fi that I calculated in my last slide and get the equation of motion of this system about the vertical axis as Note that all of the terms on the left side of this equation are a function of the relative displacement between the top of the slab and the ground. And I got this wrong, so this will be just the theta itself. So left hand side, the left hand side just shows, this indicates or is a function of the deformation of the top of the slab relative to the ground. The right hand side of the equation is basically the equivalent force applied on the structural system due to the rotational ground acceleration of the ground about the vertical axis through O. Lastly, consider the example of a 375 feet long box girder bridge on four supports, that is, two abutments and two symmetrically located bends. Each bend consists of three columns. The cross-section area of the bridge deck is 123 feet square. The unit weight of concrete is 150 pounds per cubic foot. The weight of the bends can be neglected for inertial effects. Each bend consists of 25 feet tall circular columns, and the moment of inertia, second moment of inertia of these columns about the y prime and z prime axis is a 13 feet 4. The elastic modulus of concrete is 3000 ksi. We are asked to formulate the equation of motion of the system about the longitudinal axis. Note that in the previous examples there was no damping, and there was no in some of the previous examples there was no externally applied force. So for all of those cases we know that the equation of motion simply becomes, now for the case at hand, our total weight that is considered to be lumped at the deck level is given by and the mass due to this total weight will then be given by, now 32.2 feet per second square is the value of acceleration due to gravity in feet and second units. The stiffness in the longitudinal direction due to the deformation um, will simply can be simply calculated by noting that each one of the columns will be bent in double curvature as shown in this figure, because each one of the columns is fixed at the base and fixed at the top of the box girder, and therefore so there are three columns for bent and there are two bends. The total stiffness in the longitudinal direction of the bridge is, and this comes out to be, so all that is left is that we need to plug these two values back into this master equation over there. So with this, we'll end the second lecture. Um, from the next lecture onwards, we will look into the single degree of freedom systems, mm, which are freely vibrating and do not have any damping in them, or incrementally which have damping in them, and then which do not have damping in them, all of the cases actually. So I hope you go through the examples in the book. I have represented these examples with certain degree of difficulty because it becomes really difficult to write on the screen and to make sure that the voice quality is okay. But my motivation is to actually narrate the examples a little bit. You are encouraged to solve these examples and let me know if you have any problems with this assignment or with the assignment of the solution of these example problems. Um, I'm not going to assign a separate set of problems. I would like you to solve these examples by hand and see if you're comfortable doing so. So with that, I'll see you next week. Thank you.